rotation around an arbitrary axis on the Bloch sphere. In this video, we will construct an operator which rotates a Bloch vector around an axis defined by a unit vector n on the Bloch sphere. To do that, we will use rotation operators Ry and Rz. The operator we will design will rotate the Bloch vector of a quantum state by angle alpha around the axis n. The rotation axis is defined in spherical coordinates with angles theta and phi. Let's begin. The pink arrow shows the rotation axis and the green one indicates the Bloch vector we want to rotate. First, we bring the rotation axis to the xz plane, using the Rz operator with an argument minus phi. Then, Ry operator brings the rotation axis to the z-axis. Then, we perform the desired rotation around the axis n on angle alpha and rotate everything back to the original orientation on angle theta and phi. We want to make this expression more concise. It is convenient to replace Ry and Rz operators with negative arguments by corresponding Hermitian conjugates. Now, let us apply the formula for the matrix exponential for the Rz operator in the middle. Using the algebra of the Pauli matrices, and taking into account that Ry is a unitary operator, we can expand this expression. And so, we got rid of the inner shell consisting of operators Ry. Then, using the equations we got in the previous video, we remove the outer shell consisting of Rz operators. Finally, we group the terms around Pauli matrices. In front of each Pauli operator, we have the components of vector n in spherical coordinates. Thus, we can rewrite the expression in a compact form. Since n sigma squared is equal to a unit matrix, which is proved in the video about the decomposition of the matrix exponential, we can use the exponential form for the rotation operator. So, this operator transforms a state ρ such that its Bloch vector r ρ is rotated around the n-axis by angle alpha. Or equivalently, for the state vector we can write the following expression. Since Rn can rotate a Bloch vector into any other Bloch vector, which includes all possible qubit states up to a global phase vector, an arbitrary single qubit unitary operator can be written in the following form. For some real numbers gamma and alpha, and a real 3D unit vector n. For example, consider gamma equal to pi half, alpha equal to pi, and the following direction on the Bloch sphere. Then, using the formula for an arbitrary unitary operator, we get the following matrix, which is nothing else but the Hadamard gate.